Good afternoon. Section 7.5. Strategy for integration. So today we put kind of everything together, everything we have learned about the techniques of integration. We will reiterate what we've done, kind of classify different cases, and talk about some integrals that require the application of more than one technique. Okay? Do you guys have questions? Any questions at all? Questions? No? Okay. Very good. So there are several. Do you have a question?
Small one. How hidden are the different ways we need to use, the different techniques we need to use to solve integrals?
So section 7.5 has homework problems at the end. That gives you a general, level of difficulty. And some of the even problems are pretty difficult. So you can go through several steps. And so in my experience, for midterms and finals, you will get some integrals that require more than one steps. So you should be prepared to use at least 2 steps. But so let's list the steps that we can take, right? So what can we do? So first of all, remember the elementary antiderivatives. These should come to you right away without thinking. In the book, section 7.5 gives you a bunch, right? They range from power laws to exponents to trigonometric functions, and they have things like inverse trigonometric function. For example, so do you all remember this one? What is this? Okay. You may remember the one that has a 1 here, but it makes sense to memorize this one, right? This is 1 over a, yeah? X over a, right? And another one, a similar one, dx. That's the other famous inverse trigonometric function. Stuff like that, okay? And here I put etc., right? This is not the whole list, of course. You have a whole table in the book. And you know most of them anyways. Now, technique number 2, simplification. So before you take an integral, try to simplify it as much as possible. So, for example, we can have something like this, right? So what is the step here? We have to expand the square and multiply through, right? So 1 plus 2 plus x, and one more step, multiplication through. So by doing this, I prepared the grounds for the next step, which is taking the antiderivative. Now it's ready for you to take. It's just the power function, right? Okay. If I start trying to take this integral, I may get confused. I may think, oh, maybe I should use a substitution or something like this, right? But no substitution is necessary here. You can recognize this as a sum of power functions. And those are very, very easy. Okay, so simplify as much as you can. Another example, right here. I don't know. So this is a good one. Sine plus cos squared. Okay. This looks like nothing. We don't recognize this antiderivative immediately. But again, it's a square of something, so we can expand it and see what we get. So it's sine squared x plus 2 sine x cos x plus cos squared x. Can I simplify further? Yes, by using one of the simplest identities, right? Sine squared x plus cos squared x give me 1. How about now? Is this easy? This is a lot easier, right? So I can just, I can use another identity. I can say that this is 1 plus sine 2x by remembering that this is equal to sine 2x. There is another way of doing the same integral, but let's do it like this. So we have x minus cos 2x over 2 plus c. Okay? So again, I have a full square. I expand it. I open the brackets, and I see what where I get. The next technique is, of course, substitutions. Look for substitutions. So let's consider this example. There are two ways to perform this integration. It looks very simple, and it is pretty simple. But there are at least two ways. One is to recognize that x is proportional to the derivative of the denominator. So I can use the substitution u equals x squared minus x minus 1. So du is 2x dx. And I can rewrite it as 1/2 1 over u du. So that gives me 1/2 log of x squared minus 1 plus c. Right? What if I didn't think of this substitution? What would be the other method? Say again? Secant. You could. How about last lecture? The day before yesterday?
Last lecture was bad.
That was very frank of you. I tried my best. So last lecture told you about partial fractions. Okay, partial fractions. So does this classify as a proper fraction? Yes. So we can do this. We can say that x over x squared minus 1 equals a over x minus, wait. So we can first split it into x minus 1, x plus 1, right? And then we can say that this is a over x plus 1 plus b x minus 1. And then it's very easy to find that a and b are both 1/2. Okay? So from here, I can say that my given integral is 1 over x plus 1 plus 1 over x minus 1 dx, right? And now it's easy. I have 1/2 log of x plus 1 plus log x minus 1 plus c. How come I got a different answer? Did I get a different answer? No, it's the same, because the sum of two logs is a log of a product. right? And this can be, of course, rewritten as, I should have used the absolute value, sorry. So which method is better? You can see that this is a one-liner, right? And here I even skipped some steps. I told you, oh, A and B are both 1/2, but really you had to do that. So sometimes you can make a shortcut by picking a more effective, more efficient method. Okay. And finally, what else should we remember? Look for substitution and then recognize patterns, right? So that's number 4. Recognize patterns and classify the integral. So what are we've had several lectures just going over different types of integrals. So we should be able to recognize what we have. So we have trigonometric functions, trig functions. We have rational functions, right? Rational. So we can use partial fractions. We have integration by parts. And we have radicals. So let's say trigonometric trig substitution. Okay, so you're familiar with all of these. You've seen examples, or you will see the examples when you do the homework for the corresponding sections. So in the remainder of the lecture, I'll give you a few examples of some integrals which are, for some reason, I think are interesting or instructive or something. Some of them are from the book, some of them are not. So let's look at this one. So this one is not familiar. And in this case, we actually have to use a trick. Okay. What the book says, we manipulate the integral. Manipulate the integral. So let us multiply and divide by 1 plus sine x. I multiplied and divide by the same thing. And then in the denominator, I can simplify it by writing it as 1 minus sine squared x. Right? A squared minus b squared, that kind of thing. And here I have exactly what I have. What's the next step when you see something like this? Cosine squared, very good. So cos squared x. And now we have a sum of two integrals, right? So the first integral is dx. I'm going to write it differently. Secant squared x dx, right? And the second one is sine x cos squared x dx. The first one is from the table. Right? This is just a tangent. How about this one? Substitution, right? We can see that sine is a derivative proportional to the derivative of a cosine. So we can say that u is cosine x, du is minus sine x dx. So this becomes minus du over u squared tangent x plus 1 over u, which is the same as tangent x plus 1 over plus secant plus c. Okay. So here the crucial step was to simplify the denominator. We didn't like to have a difference in the denominator. We want to replace that with one term. How did we do this? We multiplied by this, right? And that simplified the whole thing. Okay. Next example. Let's consider the following. Tangent cubed x over cos cubed x dx. So this one, there are two ways of doing it, okay? And both come from the first step, which is simplify. Okay, we are going to rewrite it in two different ways. So I'm going to write an arrow. On the one hand, we can write the whole thing in terms of sines and cosines. On the other hand, we can rewrite the whole thing in terms of tangents and secants, right? So and both give you a valid method. So on the one hand, this is tangent cubed x secant cubed x dx. On the other hand, this is sine cubed x over cos 6x dx. Okay, so very different, seemingly different integrals, and both of them can be evaluated. So how about this one? You can see that here we can reserve 1 power of tangent, 1 power of secant. So we have tangent squared x, secant squared x, tangent x, secant x dx. So this whole thing is a derivative of a secant, which suggests that I take u equals secant x. Okay, du is tangent x secant x dx. How about tangent squared? Tangent squared is secant squared x minus 1. So I rewrite this whole thing as u squared minus 1 u squared du. And now it's easy. Okay, just one more step. U to the 4th minus u squared du, u to the 5 over 5 minus u cubed over 3. And I go back. Secant 5 over 5 minus secant cubed over 3 plus c. Okay, so this is pretty standard. As long as you thought of rewriting this thing in terms of tangents and secants. Now here, is this easy? This is also easy, okay? So you observe that we can split it like this. Sine squared x times sine x cos 6x, right? And this is a derivative of a cos. So in this case, I say u equals cos x, du is minus sine x dx, which gives me 1. I also write here that sine squared x is 1 minus u squared. I can express sine squared in terms of cosine squared. So what do I get? 1 minus u squared, okay, u to the 6 du. Is this easy? This is also easy because I can divide through and I get a power function. So this is given by u to the minus 4 minus u to the minus 6 du. So it's minus u to the minus 3 plus u to the minus 5. And remembering what u was, so this is all different. So how come the answer is different? It's not different, right? You have secants and cosines. The same thing, exactly the same thing. Okay. Next. So let me see if I can confuse you. It's not going to be very difficult or not very hard? Okay. E to the 6 dx. What's that equal to?
E to the 6 times x.
Yeah. You see, because this is just a constant, right? It's not e to the 6x or anything. This. Okay. Questions? Okay. Next. 2 to the x dx. Oh, excellent. So those of you who remember the formula, that's excellent. I can never remember this formula. So I represent 2 as e to the log 2x, right? And this is, of course, e to the log 2x. And now it's easy. So this is the crucial step, right? Questions? Okay. Next, integral x tangent squared x dx. So you see this one, in this integral, we have an algebraic function meeting a trigonometric function. So the way we handle this one is we remember the identity. Tangent squared x is secant squared x minus 1. So here I'm going to have x secant squared x minus 1 dx. How does this help? Okay, this helps very much actually. So the next step I have x dx, minus x dx plus x secant squared x dx. This one is very easy. And this one requires a known and predictable method. What's the method? Second? Integration by parts. Because secant squared is a derivative of something, right? So let's write it like this. U equals x. V prime is secant squared x. So that immediately sets up my integration by parts, tangent x, right? So minus x squared over 2 comes from the first integral. And I have uv x tangent x, and I have minus tangent x dx. Okay, I'm not quite done. Question?
I was wondering, couldn't you sub for secant squared x minus 1? Like tangent to tan squared?
Oh, this is the.
Oh, okay.
So I start with this, and I believe that this substitution makes it easier. So I'd rather go this way than the other way. Okay. Because so perhaps there's another way of doing it. Okay, but I see it better this way. There's usually more than one way, but okay. So what's left? We have to. You either can remember the antiderivative of tangent, or you can very quickly calculate it. Okay, I cannot remember it, so I'm going to calculate x tangent x. So tangent is sine over cosine. Okay, so if I take u equals cosine x, then du is minus sine x is minus sine x dx. So this guy gives me minus du over u minus log u. Okay, so this is minus plus log of cos x plus c. So now I'm done. This is the answer. So the crucial step here was to recognize. So you try a few things with this, and if nothing works, then you remember, oh, tangent square is involved in this identity. Let's try to use the identity, and then you may see the light. Okay. Next example. Let's consider the following integral: e to the square root of x over square root of x dx. So what happens here? This one is actually quite easy. You can see that we have e to the something, and over here we have a derivative of that. So the obvious substitution is u equals square root of x. So du is 1 over square root of x dx, and this integral becomes e to the u d2. Thank you. Okay, and this one is easy: e to the square root of x over 2 plus c. And I have a slightly different one. How about if we don't have this convenient denominator? See, here it was very convenient to have 1 over square root of x because it provided for this derivative immediately. How about if we have e to the square root of x dx? Okay, we're going to try the same substitution and see what happens. So u is square root of x dx. So we're kind of stuck, right? We don't know what to do. Another way of handling this, sometimes when we have square roots, is to square this definition. So we have u squared equals x. Okay? So this gives me 2u du equals dx. This is a little bit nicer, although it's the same thing, if you think about it. This allows me to rewrite dx like this. Okay? So what do I get? I have e to the u, and I have 2u du. So I did manage to write it, the whole thing in terms of the new variable, except now it's not a very easy integral like this, but it's also pretty easy. What do we do to take this one? This is a standard integral that is taken by integration by parts, right? So would you like me to demonstrate how to do this?
Yes.
Yes. Okay, so let us write it like this, 2 e to the u du. So I'm going to have two variables, p and q prime. Why am I not using u and v? Because I already have u. So not to get confused, I invented new notations. P is going to be u, and q prime is going to be e to the u. Now I evaluate p prime, and the antiderivative of q is easy, right? So this becomes e to the u minus e to the u du. Okay? So, I'm sorry, u e to the, sorry, it's p times q is this one. Okay, so I have u e to the u minus e to the u plus c. Okay, so because we had a substitute for this lecture about partial fraction, I'm not sure if he explained what happens if I get confused and assign this in the wrong way. So I'm going to demonstrate what happens. So see here, I have two functions, e to the u and u. Okay, and I said my function p is going to be this one, and my derivative is going to be the other one. And then everything worked like magic. Now let's suppose that I'm confused and I got this wrong. So what would I do? I would say p, what's the other possible choice? P is e to the u, right? And q prime is u. Okay, now p prime is e to the u, q is u squared over 2. Can you see this? When I take the antiderivative. So that would be an alternative way to rewrite this integral. So applying this, we obtain the following. P times q, e to the u squared over 2 minus u squared over 2 e to the u du. Now I stand back and I think. I start from something that looks like e to the u times u. And I ended up with an integral that looks like e to the u times u squared. Is it better or worse? See, it's getting worse, which means that my mistake was here. I assigned these things in the wrong way. So I go immediately back and I change it. So it happens all the time. You may get confused and assign them the wrong way, and you see that you're getting deeper and deeper into the woods. So go back, switch them, and you follow the right path. Okay? And this in particular holds for the integrals when we have an exponent and the power. So this is the easiest of them all. It has one power of u. Okay, and this is the way. This could be u cubed. Okay? In this case, if you do it the right way, you put this is u cubed and this is e to the u, and then you reduce the power. If you do it the wrong way, the power of u will grow and only get worse. Okay? So this is a little remark on the side. Next, what do we have next? Let me do this one. This is a little bit harder. Okay. 2x minus 1, 2x plus 3 dx. Okay? Question?
Shouldn't the answer be 2 e red x?
Say again?
Shouldn't the answer be 2 e red x plus 2?
This one?
Not over 2, but 2.
Oh, you're right. Because this 2 means that dx over 2 du. Okay. So thank you. Okay, please note the typo. Okay. So here, this integral is a little bit different. Okay, and we are going to make the following substitution. Again, we have a square root, and just like here, okay, my new variable is going to be the whole square root. And the next step here was to square the whole thing, right? So we're going to do the same. Let's say that u is 2x minus 1, which means that u squared is 2x minus 1. And now this is better to differentiate. I say 2u du is 2 dx, or I divide by 2, I get u du equals dx. So this is kind of nice because I have the radical is u, dx is u du. Now I have to sort out the denominator. I can say from here that 2x is equal to u squared plus 1, right? But I don't want 2x, I want 2x plus 3. So 2x plus 3 is u squared plus 1 plus 3, which is u squared plus 4. Okay. Now we're ready to rewrite the whole thing in terms of the new variable. U times u du. And here I have u squared plus 4. Okay. Or, you know, we have u squared du, u squared plus 4. What is next? You can simplify it a little bit by one simple manipulation. I'm going to say that the numerator is u squared plus 4 minus 4 du, u squared plus 4. What does this give me? It gives me 1 minus 4 du. Okay. So now this is easy. This is simply u. And this integral I wrote down at the beginning. It's given by the arctangent. So we have 4 divided by 4, but divided by 2. Okay, tangent minus 1 of u over 2 plus c. This is this integral. So what is u? 2x minus 1 minus 2. One second, did I make a mistake here? No, it's okay, I think. 2 tangent minus 1, 2x minus 1 over 2 plus c. Question?
How did you get 2u du equal to dx? What I got is 2u du equal dx.
So
I'm not sure.
I was using this definition. Okay. So when I differentiate the left-hand side, I get 2u du. When I differentiate the right-hand side, I get 2 dx.
Oh, you just did it from that.
So, and in principle, I don't have to do it. I could derive to the same conclusion from this. But if I differentiate this, you see I have square root, it goes in the denominator, and I have to make a lot of manipulations before I arrive to this beautiful, concise answer. So when you assign your new variable to be a radical, it's good to square the whole thing. And then everything kind of follows in a simpler manner. Okay. So, question?
After you added 4 and subtracted 4, how did you get to the next integral? When you added 4 and subtracted 4 up there.
This one?
Yes, how did you get
Okay.
there?
From here to here?
Yes.
So I have u squared plus 4, u squared plus 4 minus 4, like this. So I kind of group them into this minus this minus this. Okay. More questions? Question?
How did you get to u squared plus 4 minus 4?
Which one?
The circle part, how do you get
U squared plus 4 minus 4? Oh, so if I start from here, in the numerator I have u squared. So u squared is u squared plus 4 minus 4. Nobody can argue against this, right? This is a truth, okay? And the reason I want to do it is because I want to separate 1 away, okay? U squared plus 4 minus 4 du, like this. More questions? Okay, so I want to show you one more useful example. When you do partial fractions, okay? Do you have a question?
Small one. So I do see that in these situations, using u squared, or using u as the square root of 2x minus 1 does make a lot of sense. How do we know when to use that versus the u equals 2x plus 1?
Well, if you say that u is equal to 2x plus 3 or 2x plus 1?
2x plus 1. Let's do minus 1. Sorry, man.
So you will have a square root in this integral after the substitution. And after this substitution, you get rid of the square root. And this is the reason. So if I simply took 2x minus 1 to be u, then as the next step, I would have square root of u. And I don't want it. So in this case, it's possible to get rid of the square root completely and make it into a rational function. You could always try different things. And this is one of those integrals where you sometimes have to try different things. But this is the easiest way. So when you do partial fractions, okay, with repeated irreducible nonlinear factors. This is case number 4, the last one. Let's see. So there we have repeated second. Quadratic factors. So if we have something like, I don't know, 1 plus x minus 2x squared, and here I got x like this, okay? So this classifies as case 4. Because I have an irreducible factor, I cannot reduce it anymore because there is no root to the equation x squared plus 1 equals 0. So this has to stay like this, and there are 2 of them, identical ones. So what do I do? Here I'm going to present this fraction as a over x because of the linear factor. What else do I have? I'm going to have 2 terms corresponding to x squared plus 1. bx plus c, x squared plus 1, plus dx plus e, x squared plus 1 squared. Okay? So this is the general procedure. Remember when we had repeated linear factors? For instance, if I had 1 over x plus 2 to the third power. This would end up giving me 3 terms. A divided by x plus 2 plus b divided by x plus 2 squared plus c divided by the thing cubed. Okay? The same thing happens to irreducible quadratic factors if they're repeated. If I have 2 of them, second power, then I'm going to have 2 terms corresponding to that with increasing power. If this was a third power, I would have a third term plus fx plus g divided by the cube. Okay? So this is the algorithm. And because they are quadratic factors, I don't just use a constant, but I have a linear function like this on top. So this kind of makes sense and follows from the previous 3 examples. What is slightly new here is that when we finally calculate the coefficients a, b, c, d, e, right? What would we have to, what kind of integrals are we going to have to evaluate? This one is easy, right? That's a log. This one is also easy because the first one, I can do it by the method of substitution. So the u would be x squared plus 1. This is the derivative of u. That's good. The second one is a constant divided by this. That's the arctangent. That's also good. Here, the first one, I have x divided by this thing. This is done also by means of substituting. So I would have to say u equals x squared plus 1, and that's the derivative of u. That's good. So the only new integral that we need here is a constant divided by this thing squared. So let's do that one. So evaluate the integral squared. Okay. So this integral is done by trigonometric substitution. When we recognize that we can reduce the denominator. So we say x equals tangent theta. So what follows from this? Let's see what we gain. This is secant squared theta d theta. What is x squared plus 1 in this case? That is secant squared theta. So let's write down what we got. Instead of dx, I have secant squared theta d theta. And here I have secant fourth theta. Right? Questions? So this can be simplified. Okay. Is this an easy integral? It's not secant squared. There's 1 over secant squared. So the best idea is to remember that secant is 1 over cosine. So we have cos squared theta d theta. Now we use the half angle identity. I want to represent this as cosine 2 theta. Cos 2 theta plus 1 over 2 d theta. So now this is easy. I have 1/2 theta plus sine 2 theta over 2 plus c. Okay, almost done. So let's do a little triangle, right? We have to do a triangle, I believe. So this is my theta. What do I know about theta? Tangent theta is x. So I have to put this to be equal to x, and this is 1. Tangent theta is x. Theta is arctangent of, x is arctangent of theta. And what do I need? Here I write sine 2 theta. How do I evaluate that? I remember that this is equal to 2 sine theta cos theta. So I need both sine and cosine of theta. What are they? Sine theta. That's something that I can evaluate from the triangle. What's this side? This is going to be square root of 1 plus x squared. So the sine is x divided by 1 plus x squared. And cosine is 1 divided by 1 plus x squared. Now I'm almost done. So I put 1/2 theta plus 2 sine theta cos theta plus c. 1/2 tangent minus 1 of x plus sine times cosine, x divided by 1 plus x squared. Okay, I skipped one step. Let me not skip a step. So here I have here I have sine is x over square root of 1 plus x squared times 1 plus c. So this is 1/2 tangent minus 1 of x plus x, 1 plus x squared plus c. So this is the answer. Questions? Question? So there's a half here. Oh, yes, you're right. Because there was a half here over 2. Yep. So this cancels, and I have 1/2 here. Very good. Thank you.